You are doing 70 miles an hour on I-285. You're totally boxed in my semi-trucks. The Atlanta heat is just radiating off the asphalt. Your air conditioning is blasting. And then suddenly your dashboard flashes red.
Oh man, that is the worst feeling.
Right, 0% battery, no warning chimes left. The throttle response starts to feel incredibly heavy, almost like spongy.
Yeah, you aren't really driving a car anymore at that point.
Exactly. You are now piloting a 4,000-pound, rapidly decelerating brick right in the middle of 8 lanes of hostile traffic.
Terrifying.
So you manage to muscle it over to the right shoulder just as the power steering dies entirely. You are miles from home. You're miles from a charger.
Yeah.
And you are just surrounded by concrete.
That is the modern nightmare, isn't it? I
Right.
mean, we've essentially taken the old school fear of running out of gas and given it this high-tech digital upgrade.
A very stressful upgrade.
Seriously. We call it range anxiety, but when it actually happens, when the screen goes black on the side of a chaotic interstate, it stops being anxiety and becomes a highly acute logistical crisis.
And that crisis is exactly what we are tearing apart today. We're pulling from some really illuminating source material for this deep dive, specifically a deeply technical operational handbook and service website for a company called Atlanta Mobile EV Charging.
Yeah, really fascinating documents.
And we also have a transcript from the EEE Rescue podcast detailing their expansion into the Southeast. Our mission for this deep dive is to figure out how a completely new type of roadside infrastructure is being built from the ground up to solve this exact nightmare.
Because it is a completely new approach.
It really is. We are going to look at the physics of how the technology actually works and why this business model might just quietly rewrite the rules of urban logistics forever.
So, okay, let's unpack this, because reading through these documents, I realize we are watching a massive shift in how society delivers power.
Oh, totally.
We're moving from a world where the car goes to the power to a world where the power basically hunts down the car. I love that framing. It really is a massive paradigm shift, because for the last 100 years or so, the infrastructure model has been entirely static.
Right, like a gas station doesn't move.
Exactly. The gas station is a building. The charging hub is a concrete island. You, the driver, are entirely responsible for bridging the gap between where your vehicle is and where the energy lives.
Even if your car is dead.
Right. And what we are really looking at here isn't just a roadside service, but a fascinating functional solution to the last mile infrastructure problem of the EV transition.
The last mile, yeah.
It bridges that terrifying gap between the edge of the hard infrastructure and the random patch of gravel where a real human being actually gets stuck.
And to really grasp why that gap is so terrifying, we have to look at the geography of where this service operates. The sources paint a very specific, almost intimidating picture of Atlanta.
Yeah, Atlanta's a beast.
It's not Manhattan. It is not a dense downtown core where you can, throw a rock and hit a parking garage with a level 2 charger. The service area for this mobile network covers a 45-mile radius from downtown Atlanta.
Which means we aren't just talking about a city. A 45-mile radius is a 90-mile diameter.
That is massive.
Gives a massive geographical footprint. You are essentially dealing with this interconnected web of micro-cities, endless highway loops, and sprawling suburbs that they just bleed into one another.
I was looking at the list of coverage areas in their service mandate, and it reads like a map of endless sprawl. Marietta, Roswell, Alpharetta, Sandy Springs, Kennesaw, Lawrenceville, Decatur.
Peachtree City, Douglasville.
Yeah. Conyers, Buckhead, East Point. It just goes on and on.
Right.
And navigating a web that large with an electric vehicle introduces a very specific kind of mathematical dread.
Because the algorithms in your car's dashboard assume a certain predictability.
Yeah, I got it.
The navigation system says you have 50 miles of range and the charger is 40 miles away, so you're fine. But an EV algorithm often really struggles to account for the reality of urban sprawl.
It's too unpredictable.
Right. It doesn't always factor in the sudden hour-long gridlock on the perimeter highway where your air conditioning is slowly siphoning off your battery. Or a missed exit that forces you into a 10-mile detour through suburban backroads.
I was thinking about it like a game of high-stakes musical chairs. The charging stations absolutely exist out in those suburbs, but they are highly concentrated in very specific commercial hubs.
Yeah, they're clustered.
So the chairs are there, but they are spaced 10, 15, or 20 miles apart. And if you make one wrong turn or you miscalculate your remaining range by a fraction of a percent, The music stops while you are caught in the vast empty space between those chairs.
That's a good analogy, but I would actually push back slightly on the musical chairs idea.
Oh, really?
Well, only because in musical chairs, you can clearly see where the next chair is. In this scenario, the driver often has no visual confirmation of safety.
Oh, that's true. You can't see the charger from the highway.
Exactly. You are driving past gas stations on every single corner. They are brilliantly lit, they're taunting you, but they're entirely useless to your electric vehicle.
It's almost mocking you.
It is. The visual landscape of safety that we've built over a century suddenly just doesn't apply to you. So the isolation feels much more profound.
That is such a good point, and I think anyone listening, even if you still drive a gas car, can viscerally relate to that vulnerability. Think about that creeping panic you get when your phone is at 2%.
Oh yeah, the worst.
You're waiting for an urgent text, and you're walking down a street with no outlets. You start dimming the screen, closing apps, bargaining with the universe.
We've all been there.
Now, scale that panic up. Multiply it by a 4,000-pound piece of machinery, a family in the back seat, and semi-trucks flying past your driver's side door at highway speeds.
It is a profound vulnerability. And when you finally do lose that game, when the car simply shuts down on the shoulder, the immediate question becomes, well, how do I fix this?
Right. And historically, the only answer has been to call a tow truck.
Which is where the situation usually devolves from a scary inconvenience into an absolute logistical nightmare.
Yes, the traditional safety net. The sources do a really aggressive side-by-side comparison between the old towing model and this new mobile rescue model. And frankly, the old model sounds borderline punitive.
It really does. It's rough.
Let's look at the financial damage first. If you call a traditional tow company in the Atlanta metro area, the raw data indicates you are looking at a baseline cost of $150 to over $400.
Wow.
And that is strictly for the physical relocation of your vehicle. That doesn't buy you a single volt of electricity.
You're paying a massive premium just to be moved, and then you have to factor in the time cost, which is arguably worse.
So much worse.
The service data shows that the total life cycle of a traditional EV, from the moment you make the call, to the truck fighting through traffic to reach you, loading the vehicle, driving to a charging hub, and unloading it averages between 1 and 3 hours.
3 hours on the side of the road.
Yeah.
But reading through the engineering notes, I realized why it takes so long and costs so much. It is rooted in the physical mechanics of how electric vehicles are actually built.
The drivetrain architecture.
Yeah, because I had always assumed that if a part dies, you just put it in neutral, hook a chain to the front, and drag it away. But you really cannot do that with an EV, can you?
No, absolutely not. And doing so can cause catastrophic mechanical failure. It comes down to, like you said, the architecture. In an internal combustion engine vehicle, you have a transmission with a true mechanical neutral.
Right. You shift gears.
When you shift into neutral, you are literally disconnecting the wheels from the engine. The car becomes a glorified wagon. It rolls freely. An electric vehicle, generally speaking, doesn't have a multi-gear transmission to disconnect.
So it's always connected.
The electric motors are often directly permanently linked to the axles.
So if the wheels are turning,
The motor is turning. And here is where physics becomes your enemy on the side of the road. EV motors use permanent magnets. When you force an electric motor to turn by dragging the car down the road, it acts as a generator.
Wait, really?
Yeah, it starts creating electrical current through regenerative braking.
Wait, so if you drag a dead EV behind a standard tow truck, the car is involuntarily generating electricity and firing it back into its own system.
Exactly. It is pushing high voltage current backward into an inverter and a battery management system that are entirely shut down and completely unprepared to receive or regulate that power.
Oh my gosh.
You can fry the electronics, melt components, and completely destroy the drivetrain. Because of this, almost all manufacturers strictly mandate that an electric vehicle must be towed on a flatbed.
So it can't roll at all.
Exactly. The vehicle has to be physically lifted completely off the asphalt. All 4 wheels must be stationary.
That explains the bottleneck. You can't just call the nearest guy with a hook and a winch. You have to request a specialized flatbed truck.
Which takes longer to get there.
And then once that massive truck finally navigates Atlanta traffic to find you, the driver has a deeply complex job. They have to figure out how to pull a dead, incredibly heavy vehicle up a steel incline without letting the wheels turn.
It's not easy.
Some EVs have a digital PO mode to help, but if your battery is at absolute zero, the computer is dead, meaning that digital tow mode might not even engage. It is a highly stressful, high-risk operation on the shoulder of a highway.
It is compounding stress.
Yeah.
You're hemorrhaging money, you're bleeding time, you're physically in danger standing near traffic, and you are sweating over whether the tow operator is going to damage your $80,000 vehicle.
Just a terrible afternoon.
And then we arrive at the punchline of this entire ordeal.
Oh yes, the drop-off. This is the part of the source material that genuinely made me laugh out loud at how absurd the system is.
It really highlights the flaw in the model.
After a 2-hour wait, after paying $300, the flatbed finally drops you off in a Walmart parking lot next to an Electrify America charger, and your car is still completely 100% dead.
You've just relocated your problem.
Yes, you now have to sit there, initiate a charge, and wait another 45 minutes before you can even think about driving home.
The inefficiency is staggering. You are spending hundreds of dollars and burning half your day to move a multi-ton piece of dead weight to a stationary power source.
So if dragging the battery point to the power is a mechanical and financial nightmare, the only logical workaround is to invert the model. Stop moving the car and start moving the charger.
Which brings us to the Atlanta Mobile EV charging solution. The logistics flip entirely.
According to their dispatch data, their system triggers a response in 6 minutes. The mobile unit arrives at your exact GPS coordinates within 30 to 45 minutes.
That's incredibly fast.
There is no flatbed. There is no winching a dead vehicle up a steel ramp. You stay safely locked inside your car, they pull up behind you, plug a cable into your charge port, and deliver a gentle level 2 charge right there on the shoulder.
It's brilliant.
And the entry price for this is $199.
When you look at the economics and the risk profile side by side, the value proposition isn't just better. It completely obsoletes the towing model for a dead battery.
It really does.
It takes a situation that would normally ruin your entire day, cost you a fortune, and put your drivetrain at risk, and reduces it to a minor 30-minute inconvenience.
But here's the thing. Bringing the power directly to the car sounds like an elegant, obvious solution, but it immediately raises a massive physical question.
Where does the power come from?
Yes.
Yeah.
You are parked on the gravel shoulder of I-20. There are no power lines to tap into. You aren't plugging into a pine tree. What exactly is generating that massive amount of electricity in the back of a transit van?
This is where we have to look under the hood of the operation, because the technology they're using is fascinating. And honestly, a bit counterintuitive to the entire ethos of the electric vehicle movement.
I was digging through the equipment specs in their operational handbook, and they rely on a piece of hardware called the EV Hero mobile charging unit, specifically the RH9K model.
The workhorse of their fleet.
Let me just lay out the raw numbers they provide so we have a baseline. The machine delivers 9 kilowatts of continuous output, and it can peak at 11 kilowatts. It pushes a level 2 AC charge. It utilizes a standard J1772 connector, and they carry a Tesla adapter on a 25-foot cord.
For anyone who isn't, a deep EV nerd, let's contextualize that. The J1772 connector is essentially the universal plug for electric cars. Think of it as the USB-C of the automotive world.
Got it. So almost everyone can use it.
Right. Almost every non-Tesla vehicle uses it naturally, and Teslas use a very simple adapter to accept it. And a 9-kilowatt continuous output is a very robust flow of energy.
Faster than a wall plug at home.
Oh, significantly faster than the standard wall outlet in your garage. It provides a very healthy, steady stream of power that won't overwhelm a cold battery.
Here's where it gets really interesting, though, because the output isn't the shocking part. I read the spec sheet 3 times to make sure I wasn't misunderstanding it.
You saw the fuel source.
Yes. This EV Road Hero unit, this machine designed exclusively to rescue electric vehicles and promote green energy infrastructure. It runs on a 6.1-gallon gasoline tank. It is an internal combustion engine.
Yes. They are using fossil fuels to generate electricity to charge an electric car.
I mean, we have to talk about the optics of that. Using a gas generator to charge a Tesla feels like a massive, almost comical paradox. Doesn't that entirely defeat the environmental purpose of driving an EV?
It's the first question everyone asks.
How does a company operating in the green energy space justify driving around a gas-powered engine?
It absolutely looks like a contradiction on the surface. But if you dive into the physics of emergency logistics, it is actually a masterclass in raw pragmatism. It all hinges on a concept called energy density.
Walk me through energy density, because right now all I see is an exhaust pipe charging a battery.
Think about the fundamental problem this business is trying to solve. They need to deliver a massive amount of electrical energy to a stranded car.
Right.
And they need to do it quickly, reliably and repeatedly throughout a 12-hour shift, without the rescue van itself needing to constantly stop, pull over, and recharge. Liquid fuel, like gasoline, is almost miraculously energy dense.
How dense are we talking?
A single gallon of gas contains roughly 33.7 kilowatt hours of potential chemical energy.
Okay, so a 6.1 gallon tank.
Means that small tank holds over 200 kilowatt hours of potential energy.
Wow.
To put that in perspective, that is the equivalent of carrying around two massive, fully charged, top-of-the-line Tesla Model S battery packs.
Wait, 2 whole car batteries?
Yes, but instead of weighing nearly 3,000 pounds and taking up the entire floorboard of a chassis, those 200 kilowatt hours of gasoline weigh about 36 pounds and fit inside a plastic container the size of a small cooler.
Oh, wow. When you phrase it as a weight-to-energy ratio, the physics make total sense.
Exactly. If the rescue van tried to be entirely green, if it used a giant lithium-ion battery in the back to charge the stranded cars, it would be hauling around thousands of pounds of dead weight.
And it would run out of juice eventually.
Right, after rescuing maybe 2 or 3 vehicles, the rescue van's battery would be depleted. The rescuer would then have to go find a fast charger and sit there for an hour, taking them completely out of service.
Defeating the whole point of a fast response.
By utilizing the extreme density of liquid fuel, that 6.1-gallon tank running through a highly efficient inverter generator provides enough dense, reliable energy to perform up to 10 full rescue sessions back-to-back.
It's an emergency tool, not a lifestyle. You deploy the incredibly dense energy source to solve the immediate life safety crisis on the highway, get the road cleared, and let the EV go back to charging cleanly at home.
Precisely. The macro goal of EV adoption is green energy, but emergency roadside operations require uncompromising, instantly deployable power.
But even with the physics of energy density making sense, there is another massive hurdle. And the EE Rescue podcast transcript spends a ton of time addressing it. It is the fear of the power quality itself.
The THD, total harmonic distortion.
Right. The website proudly blasts this smack everywhere, saying THD under 3%, a pure sine wave. And in the podcast, the hosts talk about how EV owners are terrified that plugging their car into a third-party, gas-powered generator is going to fry their battery, destroy their onboard computer, or instantly void their manufacturer warranty.
It's a very common fear.
So let's break down the actual electrical mechanism. What does a THD under 3% actually mean, and why is an electric car so incredibly picky about the electricity it eats?
It helps to stop thinking about an electric car as a mechanical vehicle and start thinking of it as a highly sensitive rolling supercomputer.
Okay, that makes sense.
The battery management system, the BMS, is an incredibly sophisticated piece of hardware. When you plug an EV into any power source, it doesn't just blindly open a valve and let the electricity rush in. It interrogates the power.
It tests it before committing.
Exactly. It runs a rapid diagnostic,
Okay.
it measures the voltage, it checks the frequency, and most importantly, it analyzes the stability of the alternating current. The electrical grid, the power coming out of the wall in your house, travels in a very smooth, predictable, undulating curve.
Like a wave.
That is your pure sine wave. The car expects to see that smooth wave.
So what happens when you introduce dirty power? Because I have a cheap construction generator in my garage for power outages. It runs my refrigerator fine. Why couldn't I just throw that in the back of a truck and charge an EV?
Because that cheap construction generator produces a high power, total harmonic distortion. The electrical wave it generates isn't a smooth curve, it is jagged.
Oh, I see.
It spikes, it dips, it has these micro fluctuations. It is full of electrical noise. A refrigerator uses a simple compressor, doesn't care if the power is a little noisy, but feeding that jagged, noisy power into the delicate rectifiers of an EV's onboard charger is like trying to force a square peg through a round hole at the speed of light.
So the car's computer realizes the power is jagged. What does it do? Does it explode?
No, and this is where the fear of destroying the battery is actually a bit of a misconception.
Oh, really?
Yeah, the car is too smart to let you destroy it. The battery management system acts like a digital bouncer at an exclusive club. It looks at the jagged power wave, decides it doesn't meet the dress code, and it slams the door shut.
It just rejects it entirely.
It will either violently throttle the charge rate down to a trickle, or it will simply refuse to initiate the charge entirely. It throws an error code on the dashboard and acts as a firewall.
Ah, so the real danger isn't that a cheap generator will blow up your Tesla. The real danger is that you will sit on the side of I-75 for an hour, the generator will be screaming, and your car will stubbornly refuse to accept a single drop of electricity because it is protecting itself.
That is the exact operational failure this company had to solve. And that is why the EVR Hero specification of THD under 3% is the linchpin of their entire business model.
Because under 3% is exceptionally clean.
It is practically identical to the smooth, stable sine wave of standard residential grid power. The car's internal computer runs its diagnostic, analyzes the incoming current, determines it is perfectly safe, and opens the gates to accept the full 9 kilowatts of continuous power.
It doesn't even know the difference.
The vehicle software literally has no way of knowing. It is not plugged into a premium wall charger in a luxury garage.
Clean power is clean power. The car just sees the smooth wave and goes to sleep. That completely demystifies the technological fear.
It really does.
And speaking of fear, there is one other detail in the hardware specs that I found fascinating, mostly because it shattered my mental image of what this rescue actually looks and feels like.
You're referring to the acoustics.
Yes. When I picture a gas-powered generator capable of pushing 9,000 watts of continuous power, I picture this deafening, violently vibrating industrial monster roaring on the side of the road.
Like a construction site.
Exactly. I picture having to wear ear protection just to stand next to it. But the engineering sheet lists the acoustic output at exactly 64 decibels from a distance of 23 feet.
Which is remarkably quiet. To ground that number in reality, 64 decibels is roughly the ambient volume of a normal human conversation in a quiet restaurant.
Or like the hum of a modern dishwasher.
Yeah.
It is quieter than the traffic flying past you on the highway. That completely changes the emotional atmosphere of the rescue. You aren't standing next to a screaming piece of construction equipment.
You can actually think clearly.
You're just standing by the bumper, having a calm conversation with the technician, while this quiet, enclosed unit gently hums and feeds clean power into your vehicle. It takes a chaotic, terrifying scenario and injects a sense of total engineered control.
It calms the driver down. And once you have calmed the driver down, once they realize the tech is safe, the power is clean, and the machine isn't going to deafen them, the immediate next thought they have is, well, how much is this going to hurt my wallet?
Which brings us perfectly to the consumer playbook. How does a stranded driver actually interact with this service, and how do they choose what they need? Because the AtlantaMobileEVCharging.com website doesn't just offer a charge.
No, it's very structured.
They have a very specific menu-driven tiered pricing system.
The psychology behind their pricing architecture is brilliant, specifically because of how they frame the entry-level tier.
Let's walk through that menu for everyone listening.
Sure.
Tier 1 is called the Quick Boost. It costs $199. It guarantees 30 minutes of charging time, which mathematically equates to approximately 30 to 40 miles of range added to the battery. And crucially, it is highlighted on the site as their most popular option.
Right, that's key.
Tier 2 is the standard charge. This jumps up to $329 for a full 60 minutes, delivering about 80 to 100 miles of range.
A bigger jump.
And Tier 3 is the extended charge. $429 for 90 minutes, giving you roughly 130 to 160 miles of range.
Okay, and the fees?
Right, there are two highly transparent fees. An after-hours fee of $50 if you call between 6 p.m. and 6 a.m., and an extended travel fee of $2 per mile if your GPS location is outside their standard 25-mile base radius.
Let's focus on that Tier 1 Quick Boost. As a consumer, your initial instinct might be to look at that menu and think, well, if I'm totally dead, I want as much range as possible. Why would the lowest tier, the one that only gives me 30 miles, be the most popular?
Right. Why not fill it up to 80 miles just to be safe?
Because you have to consider the mindset of the stranded driver. This service is engineered as an emergency off-ramp, not a replacement for your home charger.
They just want to get off the road.
Exactly.
Right.
The driver on the side of the road is in acute crisis mode. They are not looking to top off their battery to 100% so they can embark on a cross-country road trip. Their only goal is to make the immediate physical danger disappear.
They just want to limp to the nearest working Electrify America station, or ideally just make it back to their own driveway.
And in a sprawling metro area like Atlanta, 30 to 40 miles of range is mathematically sufficient to navigate out of the danger zone and reach a safe harbor from almost anywhere within that highway web.
That makes total sense.
The $199 price point is perfectly calibrated to be the ultimate rational choice. It solves the core problem getting you off the dangerous shoulder as fast as possible for the lowest possible price. That is why it captures 90% of their emergency calls.
It's the price of a really nice dinner for two, but it buys you your safety and saves your afternoon, which explains the existence of the higher tiers.
The standard and extended options.
Yeah, they aren't meant for the guy who died on his commute in Buckhead. They are there for specific severe outliers. If you are deeply outside the city limits or you are in the middle of a long interstate journey down to Florida and the nearest fast charger is literally 60 miles away, you have the option on the menu to buy that extra time and range to bridge the massive gap.
It offers flexibility for worst-case scenarios, but the foundation of the business is built on the high turnover efficiency of that 30-minute quick boost.
And I really have to highlight the transparency of this menu. Compare this to the psychological dread of the traditional towing industry.
It's night and day.
Calling a tow truck often feels like dealing in dark arts. The dispatcher quotes you a $50 hook fee over the phone, so you agree. Then the driver arrives, and suddenly there is a $5 per mile transport fee, a specialized flatbed surcharge, maybe a storage fee if it's late, and suddenly your $50 quote has ballooned into a $400 nightmare, and they're basically holding your car hostage until you pay.
It's an inherently predatory structure because the consumer has zero leverage once the car is on the truck.
Exactly. But with this mobile charging service, it is a flat, menu-driven retail transaction. You know exactly what the financial damage is before the van even shifts into drive.
It removes the guesswork.
It completely removes the secondary anxiety of financial uncertainty during an event that is already maxing out your stress levels.
And that transparency extends to the after-hours fee as well, which is an interesting psychological pivot.
The $50 charge between 6 p.m. and 6 a.m. on a normal Tuesday afternoon, paying a $50 surcharge might annoy you.
Sure.
But I want you, the listener, to really put yourself in this scenario. It is 2 a.m. You are on a dark, unlit, unfamiliar stretch of highway outside Decatur. Your battery is dead. The dash is dark. You are panicked.
It's terrifying.
What would you be willing to pay in that exact moment to have a trained professional arrive in 30 minutes, plug in a quiet machine, and simply make the entire terrifying problem vanish?
In that context, a $50 premium doesn't feel like a penalty. It feels like an absolute bargain for your safety. It is the cost of absolute convenience in the middle of the night.
So the consumer roadside rescue side of this business is undeniably the most dramatic. It has the flashing amber lights, the highway shoulders, the literal rescuing of stranded families.
The hero moments.
Right. But reading through the subtext of the EEE Rescue podcast transcript, it becomes incredibly clear that consumer rescue is actually not the most transformative part of this company. In fact, it might not even be the most lucrative.
Not by a long shot. The consumer side is the public face. The true paradigm shift. The thing that could actually alter the mechanics of urban commerce is happening quietly behind the scenes.
We are talking about the B2B side, the stealth empire of fleet charging.
If we zoom out and look at Atlanta's macro economy, it is fundamentally a massive logistics and distribution hub. The sheer volume of goods, services, and humans moving through that 90-mile diameter every single day is staggering.
The sources explicitly list the types of businesses they are targeting. We are talking about last-mile delivery fleets, the vans dropping packages at your door.
Yep.
We're talking about rideshare drivers who need to stay on the road to make a living, massive corporate vehicle pools, rental car companies at Hartsfield-Jackson Airport that need to constantly turn over inventory. And all of these businesses across the board are aggressively transitioning their fleets from gas to electric.
And they are not transitioning because they suddenly want to save the rainforest. They're transitioning for a very simple, ruthless reason.
Economics.
Economics. Electric vehicles have significantly lower operating expenses per mile. Electricity is cheaper than gas, and EVs have drastically fewer moving parts. No oil changes, no transmission fluid, fewer brake replacements due to regenerative braking.
Yeah, it adds up fast.
For a fleet operator running 50 delivery vans, that reduction in operating expense per mile is financially irresistible.
The math makes it a no-brainer, but there is a monumental catch, and the podcast transcript highlights this bottleneck perfectly.
The infrastructure barrier.
Right. When a business decides to electrify its fleet, they usually think they are just buying new vans. What they suddenly realize is that charging infrastructure is not just a purchase. It is a massive, highly regulated construction project.
Let's walk through a hypothetical to show just how painful that construction project actually is.
Okay, let's do it.
Imagine a medium-sized plumbing company in Atlanta. They have 20 vans. They lease a warehouse in an industrial park